This is a computer assignment presentation by Juliet Mora. First, we'll be identifying the internal components of a central processing unit. The central processing unit, also known as the CPU, this is the brain of the computer that carries out the computer's instructions before executing basic arithmetic and output or input operations. It controls the operations of all parts of the computer. The CPU internal space are made up of several components that work together to perform a specific task. This is an example of a CPU, but there are many types of a CPU, but I chose the Core i5, which is shown on the diagram. The next thing we'll be looking at is the components of the central processing unit, which the first one is the arithmetic logic unit, the ALU in short form. It performs arithmetic and logical operations such as addition, subtractions, comparisons, and logical operations, which is AND or. It acts as a gateway between the primary memory and the secondary storage. It is classified into two, the arithmetic section and the logic section. This is an example of how the ALU looks like in the diagram. This is the second component of the central processing unit, which is the control unit. The control unit fetches instructions from the memory, then decodes the information into binary instructions, which are understandable for the CPU to execute those instructions in the correct order. It manages the timings and the control signals of the CPU. This diagram shows how the control unit works with the flag and the clock to send signals to and from the control bus. At the third component, we have the registers, small high-speed storage locations directly within the CPU. These registers temporarily hold data and instructions during processing. Common types of registers include the accumulator, which is also known as the ACC. It stores intermediate results of operation. We have program counter, the PC. It holds the memory address of the next instructions to be executed. Then we have the instructions registers, the IR. They hold the current instructions being executed. The memory address register, MER, stores the address of the memory location to be accessed. The memory data register, the MDR, it stores the data being transferred to or from the memory. In this diagram, it shows a von Neumann system and how the registers work with the memory to hold data that is frequently used by the CPU. This is the fourth component of the CPU, which is the cache memory. This is a small high-speed memory located inside or very close to the CPU. It stores frequently accessed data and instructions to reduce access time to the main memory, which is the RAM. It is typically organized in levels of L1, L2, and sometimes L3. In this diagram, it shows the interior of the computer where the cache memory is located. The fourth component of the CPU is the clock. It generates regular pulses measured in hertz to synchronize the operation of all components within the CPU. The clock speed determines how many instructions per second the CPU can process. On this slide, we have the buses, which are a set of electrical paths that transfer data, addresses, and control signals between different parts of the CPU and other components, which help the control unit to do its job. They include the data bus, which transfer actual data, the address bus, which carries memory addresses, and the control bus, which carries control signals from the control unit. In this diagram, it shows the system buses and how they work together. The control bus is bidirectional. It carries signals from the CPU to all other computer components, for example, the memory, which is shown in the diagram. The data bus is also bidirectional. This means it can carry data from the CPU to the memory vice versa, as well as to and from the input and output devices, which is shown in the diagram. Address bus is unidirectional. Data is only carried from the CPU to the memory. In this slide, we're going to see an explanation of the functions of the CPU. The central processing unit is often referred to as the brain of the computer. It performs the essential tasks that allow the computer to run programs and respond to the user inputs. The main function of the CPU is to execute instructions provided by the software and manage the flow of data through the computer system. Here are the main functions of the CPU, which will be shown in the next slide. The first function of the computer is the fetching instruction. The CPU retrieves or fetches instructions from the computer's memory, which is the RAM. This is done through the program counter, known as the PC, which keeps track of the location of the next instruction in the memory. The fetch instruction is taken and stored in the instruction register. The second function is decoding instructions. This is when an instruction is fetched and then sent to the control unit, which is also known as the CU. The CU decodes the instruction to determine what operation needs to be performed, for example, maybe addition or data transfer. The decoding process converts binary coded instructions into control signals that direct the CPU components. After decoding instructions, the instructions are then executed. The Arithmetic Logic Unit, the ALU, carries out the decoded instructions that involve arithmetic or logical operations. This may involve performing arithmetic operations, e.g. 2 plus 2, making logical comparisons, e.g. is A is greater than B, or moving data from one register to another. In this diagram, we're going to see how the address is fetched from the memory unit, then decoded, and passed as a control signal to the components within the computer system. The next function of the computer system is storing results. After execution, the results may need to be stored back into the memory or a register for further use. This is handled via the memory data register, also known as the MDR, and the memory address register, also known as the MAR. On this slide, we're going to explain how the computer hardware components work together. The CPU performs all the processing tasks in a computer. It fetches, decodes, and executes instructions. The RAM, also known as a random access memory, holds data and instructions that the CPU needs while performing tasks. Devices like hard disk drives, also known as HDDs, or solid-state drives, also known as SSDs, store data and programs permanently. The motherboard connects all components together, such as the CPU, RAM, storage, input or output devices. Devices like keyboard, mouse, scanner, and the microphone let the user input data. And devices like monitors, printers, and speakers show the results of the processing. In the current slide, we'll be identifying different types of storage media and explain the use of each with its references to the purpose. The first one will be magnetic storage devices, also known as the hard disk drives. It is used to store data which can be used as a backup. It has a large capacity of storage. One of the storages is primary memory. It stores operating system, software, and user files. Data is stored in digital format and magnetic surfaces of the disk. It uses platters which can spin, and data is also stored on the surface of the sectors and the tracks within the platters. This diagram, it shows the interior of the hard drive, and where we can see the orange part is also called the platter. It is divided into tracks and sectors as previously discussed on the previous slide. The second storage media is known as the solid-state device, also known as the SSDs. This is a storage device that stores data by using integrated circuits, offering a faster and greater durability than that of the traditional hard drives. It reduces problems in latency, which in other words can be known as maybe lagging in the system, or the time taken to find the track on the hard disk. No moving parts, hence faster than the HDDs in reading and writing. Data controlled movements of electrons by using NAND chips. Tiny transistors store the data in form of zeros and ones. Junction of one transistor is called a gate. First translator is floating gate. The second transistor control gate, one it uses grids and columns and rows two transistors at each intersection. They are non-volatile, best for quick boot time, faster uploading, and performance at tasks. This image, we'll see an example of a solid-state device, also known as a flash disk. The third storage media is the optical storage devices. This is a form of storing data by using laser lights to read and write information on the disk's surface. The uses are backing up files and documents. The drive motor is used to spin the disk. They are used for storing and playing music in CDs. They are also applicable for transferring large files between computers. They are also used for storing and watching movies. In this slide, we're going to explain how data is represented in computer systems. Computers are electronic devices that process and store data. However, they cannot understand letters, numbers, or images in the way humans do. Instead, all data inside a computer is represented using binary coding, a system of only 2 digits, which is zeros and 1, known as bits, which is also known as the machine language. Normally, nits are grouped into larger units like 8 bytes, which represent different types of information. The binary system, also known as the base 2 number system, is a system that only uses 2 digits, 0 for off and 1 for on. These digits are referred to as bits. All types of data, numbers, images, sounds, and videos are usually converted into binary code before being processed or stored in a computer. Next, we have the decimal number system. The decimal number system is also known as the base 2 number system. It uses 10 digits, which are represented by the numbers 0 to 9. The hexadecimal number system is known as the base 16 number system. The digits are used from 0 to 9, and they use letters as well. The letters are between A and F, which will be shown in the next slide. This table shows a clear representation of hexadecimal letters and how they are represented. In this slide, we'll see how the data is represented. A bit is the smallest unit of data in computing. It represents one of two values, 0 or 1. 8 bits is equals to 1 byte. 1 byte can be represented in 256 different values, from 0 to 255. Larger units include kilobytes, megabytes, gigabytes, and terabytes. The KB is equals to 1024 bytes. The MB is equal to 1024 kilobytes. The GB is equal to 1024 megabytes, and the TB is equal to 1024 gigabytes. In this slide, we'll be explaining about the bitmap images. Images are made up of pixels, which are tiny dots. Each pixel's color is represented by a binary code. The color values often use the RGB model, which is the red, green, and blue, with each component represented by 8 bits totaling 24 bits or 3 bytes per pixel. Sound is represented by sampling audio waves at regular intervals. Each sample is converted into binary value representing the amplitude, also known as the loudness. Higher sampling rates and bit depths means better sound quality. Videos are a series of images or frames shown quickly to create a motion. Each frame is encoded like an image and audio is synced with it. Compression, e.g. the MP4, reduces the binary data needed for efficient storage and playback. In this slide, we're going to explain how encryption can be used to represent data. Encryption is a process of taking a plain text, like a text message or email, and converting the information to prevent unauthorized access and making the document unreadable, which is known as a ciphertext. This helps to protect the confidentiality of digital data, either stored on a computer system or transmitted through a network like the internet. Encryption is divided into two: symmetric encryption and asymmetric encryption. The symmetric encryption uses the same key for both encryption and decryption. It is fast and efficient, suitable for large amounts of data. Example is the IES, Advanced Encryption Standard. Asymmetric encryption uses a public key, cryptography, for encryption and private key for decryption. More secure for transmitting data over the internet, for example, the RSA, Reverse Shamil Ad-Diman. Encryption is important, one, because of data privacy. It keeps sensitive information such as passwords, emails, and bank details private by transforming it into a ciphertext. Data integrity ensures that data has not been altered with or tampered with. They secure communication. They protect data during transmission over networks, e.g. emails, websites, and messaging apps. By using protocols such as HTTPS, authentication helps with the identifying of users or systems and whether the data has been altered with. On this slide, we'll be seeing how images and sounds are represented in computer systems. An image on a computer is made up of tiny dots called pixels, short for picture elements. Each pixel represents one color, red, blue, and green. A higher number of pixels, which is also known as resolution, means a clear and more detailed image. The most common color models are RGB, red, green, and blue. Each pixel is a combination of 3 colors, and each color component is usually stored using 8 bits, which is equal to 1 byte. This means that a single pixel often requires 24 bits equal to 3 bytes, 8 bits for red, 8 for green, and 8 for blue. Data is stored in different formats. One is a JPEG, where the photos are compressed and loses some detail, which uses lossy compression. PNG supports transparency and uses lossless compression. BMP is uncompressed and usually very large. GIF supports simple animations with limited color range. Sounds are represented in different formats. A, we have sampling. Sound is naturally analog in nature, but computers need it to be in digital form. The process of converting sound into digital form is called sampling. Sampling captures the sound wave at a regular intervals. The example is shown how it usually is. On this slide, we'll talk about the sample rate and the bit depth. Sample rate is how many samples are taken per second, which are measured in hertz. For example, 44,100 hertz is equals to 44,100 samples per second. Bit depth is how much data is used to store each sample. Higher bit depth means more accurate sounds, and CD quality audio uses 16 bits per sample. On this slide, we'll be explaining how compression can aid the storage of data, images, and sounds. Compression is the process of reducing the size of data so that it takes up less storage space and can be transmitted more quickly. It is commonly used for files, images, audios, and videos to save up the space and improve efficiency without significantly affecting the quality. Compression is divided into two. One is the lossy compression and the lossless compression. Lossless compression will be the first compression we'll be talking about. This is a compression technique where the file size can be reduced without the loss of the original data during compression. Unlike lossy compression, the data can be restored back to its original form. Some of the examples include text documents, software files, and some images. Lossy compression is a compression technique that works by reducing the data size by permanently getting rid of some original data. Once the data has already been compressed, it cannot be reversed. Some of the examples are photos, music, and videos. Compression is important because it saves up storage spaces on devices such as phones and computers. Number 2, it speeds up file transfer and downloads. Number 3, it reduces internet bandwidth and usage. It also makes backups and achieves more efficiency. Compressed audio and videos are able to stream more smoothly. On this slide, you're going to see the purpose of the logic gates. They are used to perform logical calculations on binary inputs. They control the flow of electric signals and control the operations in the computers. The gates help by processing information and making decisions and performing calculations. Examples include AND gate, which says yes when two of the inputs are ones, the OR gate, which says yes if any of an input is a 1, and the NOT gate, which says yes if any of the input is a 0. On this slide, we are going to see the diagram representing all the logic gates, which is the NOT gate, AND gate, NAND gate, OR gate, NOR gate, exclusive OR or exclusive NOR, and showing their inputs and outputs. Here we'll be describing the purposes of different types of computer networks. Number 1 will be the LAN, also known as the local area network. It connects devices in one building like home, school, or even the office place. It works fast and has a low expenses as you use little wires. WAN is also known as the wide area network. It connects devices in a large geographical area such as cities and countries. It connects many LANs together. The internet is the biggest one. Places WAN is used are areas like businesses, ISP, and the government. Continuation of the types of computer networks. MAN, also known as the Metropolitan Area Network. It connects multiple LANs together in the same city. MAN is bigger than the LAN but smaller than the WAN. Places manned are used at universities, city government, city company, businesses with multiple buildings in the city. PAN, also known as the Personal Area Network, it connects devices close to each other belonging to one person, e.g. the smartwatch or even headphones. Places PAN are used at anywhere that it connects devices using Bluetooth cables or even airdropping. WLAN, Wireless Local Area Network, it is a LAN that connects devices without using wires, e.g. the Wi-Fi. Describe the hardware, software, and transmission media used in computer networks is what you'll be viewing from this slide. Hardware devices, this is a physical device that connects and manages networks. For example, number one, you have the router. It connects devices and allows data packets to be between different networks. It also converts data to different protocols and formats. It acts as a default gateway. It calculates the shortest route for packets to use. Modem, also known as the modulator or demodulator. Modern computers work with digital data while many of the public communication channels use analog data. Hence, data needs to be converted from digital to analog using modem. At number 3, we have the repeater. When signals travel a long distance, they suffer from a signal problem. A repeater boosts the signals, making it stronger, hence it can travel a larger distance and reach. Hub is the fourth one. They are hardware devices that can have a number of devices with computers connected to them. They send data to every computer after receiving it from one of the ports. The switch are almost the same as the hub. The difference is the way they transmit data. It checks the packet and sends it to its destination. This is an example of a router. This picture shows the example of modems. This is an example of a repeater. It boosts weak signals. This is an image example of the hub that connects computers. This is an image example of the switch. Software devices are devices that connect and manage a network but cannot be seen physically. For example, we have the operating system such as Windows, Linux, and the Mac OS. They support networking tasks like sharing files and internet access. Firewall software protects the network by filtering what comes in and what goes out. Network protocols are rules for communication such as the HTTP and the TCP. Antivirus protects it against viruses in the network. Transmission media is a pathway of how data is carried. It is either wired or non-wired. Wired are twisted pairs of cables mostly used for LANs and has a low data transfer rate. They are affected by external interfaces which are cheap. Coaxial cables are used mostly for MANs and cable TVs. The rate of transfer is 80 times better than the twisted pair. They are more expensive than the twisted pair. Fiber optic cable covers a long distance and uses pulse of light. It is best to use as it has a high resistance of external interfaces which are expensive. Wireless, the radio waves, Wi-Fi, and Bluetooth. The microwave used for long-distance communications, into brackets, satellites. Infrareds are used for short distance like TVs. This is an image example of twisted cables, which is followed by an image example of coaxial cables. This is a clear image example of fiber optical cables. Ranges of World Wide Web technologies include number one, the web development programs. They are used to build up web pages and websites. For example, we have the HTML, also known as the Hypertext Markup Language. It forms the content of a program or a web page. Number two, we have the JavaScript, used to adapt the graphical and dynamic of the web page or a program. The CSS, also known as the cascading style sheets, organize the layout of the program or the web page, how it will be arranged, in other words. Number two, we have the web browsers. It allows users to view, access, and use web pages, e.g. the Google Chrome, Mozilla Firefox, and the Microsoft Edge. At number three, we have the web server. It runs websites and transfers information content to the user through the internet. The protocol identifies the rules for the data communication through the web, for example, the HTTPS, also known as the Hypertext Transfer Protocol TCUA. It is used for loading pages like FTP, file transfer protocol used for download and updating files. At E, we have the database. It stores and manages data used by the website and the web application. The web application program interface allows websites to communicate or interact with other apps or servers. On this slide, we're going to identify the different types of computer network topology. Network topology refers to the physical or logical arrangement of devices like computers, routers, or switches. In a network, the way the devices are connected affects the network's performance, reliability, scalability, and ease of troubleshooting. At first, we have the bus network. It uses a single central cable to which all computers and devices are connected to it. Data travels in one direction, is a peer-to-peer model. It can be used to store data and transfer data. Other users on the network can also access data from another node. It is used in an office environment. At number 2, we have the star network, also known as the client server. It uses a central hub/switch on all devices/computers and are connected to the hub. Each device has its own dedicated connection to the central node. It is as secure as the central server and sends a packet to the node that has a matching address, the recipient address in the packets. Mesh networks are divided into two types, the routing and the flooding. Routing works by nodes acting like routers so that data is directed to the shortest destination. Flooding sends all data by all nodes, no routing logic. The hybrid network is a mixture of two or more different topologies, into brackets, packets. This is an image example of the star network. As you can see, all the computers are connected to the central server. This is an example of a bus network and all computers are connected to one wire. In this image, every computer is connected to each computer in the network, which shows an example of how a mesh works. This is an image example of a hybrid network. It shows a bus network and a star network. And this comes to the end of my presentation. Thank you for listening.